Algorithms Video 1. Have you ever wondered that there are differences in the route which you usually take and the one which GPS shows is the shortest? Is it due to the algorithms used, or is it just that the GPS is not so smart? I learned from my graph theory data structure classes that breadth first search, also known as BFS, is used in GPS navigation and digital maps. And when I asked for explanation, I was asked to leave the class quietly. To the day I decided looking for the possible use of algorithms, be it breadth first search, example, or A-star application use in GPS navigation. Let me share what I learned. Before you begin with breadth first algorithm use, you need to understand how GPS navigation actually works. Digital maps, unlike humans, see streets as a bunch of nodes. The 2.6-mile road from the Columbus Circle Station, 59th Street, to Cathedral Parkway, 110th Street, is called Central Park West. We humans consider this road a single entity. You may divide it into few more segments based on metro stations or intersections, but not more than that. But a GPS navigation or any other digital map, not being so smart, divides it into hundreds of segments, some only 24 meters long. A GPS looks at the street as a graph divided into vertices and edges. Consider this. There is a lot of data to be covered and calculated while finding the shortest path. Now, before we begin, you must know the answers to the following. Don't worry, it's not a test, it's just a recap. So, what is a graph? A graph usually looks like this and is made up of vertices and edges represented by lines and circles respectively. The objective of a graph is to represent a problem as a set of points that are connected in various ways using edges. With the help of such graphs, we tend to solve our problems by applying various algorithms. Facebook is a good example to understand graph theory. Facebook has millions of users. If a person needs to find a friend, he can use an array and search technique. But that would take a lot of time and memory to search for so many people, making the problem quite complex. But if the same scenario is represented using a graph, the problems tend to get solved easily. With a graph, you know that these two people are actually friends, though real-life scenarios are not exactly that simple. Graph theories are frequently used in various other fields, such as maps, e-commerce, and computer games. You can read more about the graph theory by clicking on the link below. It explains important aspects of graphs, such as directed, undirected, cycle or loop, and matrix. Next, we need to discuss the difference between a graph and a tree. It's pretty simple. A tree can be termed as a special type of graph, a minimal graph, where there's only one path between two vertices. Now, we finally come to the important discussion of what is breadth first search and how does it work. Depth first search, DFS, and breadth first search, BFS, are algorithms, or in simple terms, they are methods to traverse a graph. Consider this example. Take a graph with 13 nodes. When breadth first search is applied to this graph, the algorithm traverses from node 1 to node 2, and then to nodes 3, 4, 5, and 6 in green, and so on in the given order. If you consider 1, in red, as the first node, you observe that breadth first search gradually moves outward, considering each neighborhood node first. This eventually brings us to the accepted definition of the breadth first search algorithm. Breadth first search, BFS, is an algorithm for traversing and searching tree or graph data structures. It starts at the tree root, or some arbitrary node of a graph, sometimes referred to as a search key, and explores the neighbor nodes first before moving to the next level neighbors. So how is this related to graph traversal in maps? Now, for this grid shown, there could be n number of ways to traverse from point A to point P. We decide to consider only 2 of these n ways. So how does an algorithm decide which is the shortest way to reach a destination? Graph traversal algorithms. The breadth-first search algorithm looks at the map as we do, it just can't perceive it completely. So when you have to travel from one destination to another, you draw a line from point A to point B, and then choose the road closest to that line. Algorithms repeat the same method, choosing the node nearest to the intersection points, eventually selecting the route with the shortest length. Let's take a simple example of grid world given above and try solving it using breadth-first search. Assume you need to travel from location A to location P. For understanding, every vertex in the image is a given number, which is the total distance from the source, and an alphabet which represents the previous node. Step 1. Visit neighboring nodes to A, i.e. B, E, and F. The vertex to B would become 1 minus A, and since E and F are also at an equal distance as B, vertices to both E and F from A could be denoted as 1 minus A as well. There is no particular order for node preference, but to make it simple, we began with B. Step 2. Since all the neighboring nodes of A have now been traced, we will mark A as visited and take the next visited node as the source node, which in this case is node B. Now visit all the adjacent nodes to B, which are C, 2B, and G, 2B. Since node F is considered in the previous step from A, therefore it need not be visited again. Once all the neighboring nodes from one node are visited, mark them as visited and move to the next step. Step 3. Visit all neighboring nodes of node E, which are I, 2E, and J, 2E, and mark E as visited. Step 4. Visit neighboring nodes of F, which is K, 2F. Since all adjacent nodes have been visited by either B or E, mark node F also as visited. Step 5. Repeat the process until all the nodes on the grid are visited at least once. Step 6. Once all nodes are visited, you would find that the distance required to reach from A to P is 3, and the shortest route is diagonal. Ah, you knew that already. Now, remove all the vertices which are not used to connect the nodes, as in the graph above. Such graphs are called minimum spanning trees, where each node is connected to at least one vertex. But, as the saying goes, in the real world, you can't always move diagonally. Most of the portions in between the intersection are occupied by houses, shops, malls, and metro stations. So how does BFS work in such circumstances? Let's understand it with the same grid world example, but in this case, the algorithm is not allowed to move or visit a node diagonally. Step 1. Consider node A as a source and visit all neighboring nodes of A, which are B, 1A, and E, 1A. Mark A as visited. Step 2. Visit all neighboring nodes of B, node C, 2B, and node F, 2B, and mark B as visited. Step 3. Visit neighboring nodes to E, since F is already visited by B. Visit node I, 2E, and mark E as visited. Step 4. Repeat the steps for all nodes until each of them has been visited at least once. Mark nodes you considered visited. Step 5. Remove all the unconnected vertices and convert the graph into a minimum spanning tree connecting each node at least once. Highlight the nodes connecting source node A to node P, which has the distance 6 and is the shortest path between two nodes. You now might have understood why GPS navigation didn't suggest the path A, E, I, M, N, O, P, or A, B, C, D, H, L, P, though they were equidistant. Once you've understood the way GPS navigation works, you'd wish the world could be a simple grid, but to a programmer's disappointment, it isn't. Hence, for a GPS, distance is not the only factor in choosing a route. Rather, elapsed time, the speed limit on a route, live traffic updates, and the number of stop signals all have to be taken into consideration. That's why you would find your GPS occasionally suggesting winding state highways to travel instead of the usual national highways. Most of the GPS or digital maps have evolved over breadth-first search to A-star algorithm. You can read more about A-star algorithm here. due to better complexity over a period of time. Yet, GPS is one of the most amazing devices. Connected to satellites 12,000 miles above the planet, it calculates your position in real time with more than 5 million possibilities for a particular route.